Okay, so today's session is about vapor power cycles. But before that, let's we go what we have done in the previous session and remember what we have done there. And I will highlight some of the important stuff that we will be needing for this today's session. Right. So, so the last time we discussed about different laws of thermodynamic. Under there, we have discussed the first law of thermodynamic. Right. So the first law of thermodynamics. So this is one of the important things. Right. So delta U equal Q minus W. Right. Delta U is the enthalpy change. Sorry, the internal energy change. Internal energy change equal to net heat minus net work, right? So we will be using this equation today, right? Then we discuss about the conversion. The heat plus to the system, heat addition is plus, heat rejection is minus, uh, work done on system is minus, work by the system is plus, right? So this conversion is important, right? So then we discuss about enthalpy, right? So enthalpy is equal to H, enthalpy, H equal U minus PV, right? So U is the internal energy here, right? Internal energy and product of pressure and volume, right? And also this one is important, right? The enthalpy is the measure of total heat energy absorbed or released in a thermodynamic cycle. So the enthalpy is a total heat energy, right? Total energy rejected or absorbed during a thermodynamic cycle. So this one also important point. So we will be using this one today as well, right? Then we talk about the second law of thermodynamics, and there we discuss about two statement, Clausius statement and the Kelvin-Planck statement, right? So if you remember, I hope you remember these two things. If you have not gone through this lecture, please go through it. Otherwise, you will be not be able to understand this session, right? So then we talk about the entropy, right? So entropy is the total disorders of the system, or we call the randomness, right? Then we talk about something called isentropic process, right? Isentropic process. Now this is also an important point. So isentropic is a special type of adiabatic process, right, where there is no entropy change, right? Entropy change, there's no entropy change. Entropy is a constant, right? We call that one as a isentropic process, right? Then we discuss about third law of thermodynamics. Then at the end we talk about heat engine. So there are two types, heat engine and heat pumps. The first thing we have discussed about heat engine and the efficiency of the heat engine. So again this one is important one, right? Heat engine is equal to W net minus Q in. W net means W out minus W in, right? So that is W net, and Q in is the heat that we added to the system, right? Q in. So W out minus W in divided by Q in. So this is the efficiency for a heat engine. So right. So we will be using this equation today as well, right? Right. So let me come back to today's session. So today's session is about vapor power cycle. So under there we will be discussing uh, two cycles. One is the Carnot vapor cycle, right? So we have here the Carnot vapor cycle. This is the one, Carnot. Then we're going to discuss about the Rankine cycle, right? So before going into that, let me look at the diagram of thermal power plant, right? So what you seen in here is a basic diagram of a thermal power plant, right? Now why we call thermal power plant? Because the thermal power plant convert thermal energy or the heat energy into work, right? Okay, so we have heat into electricity or work at the end, right? Or at the end electricity. right? So this is the conversion. Now let me go step by step, right? So now this picture is for a coal power plant, right? Coal power plant, why it is coal? Because the fuel is the coal, right? So the coal is the one that generate or use as the fuel to produce heat energy, right? So there can be different names. For example, if you are using a coal, we call it a coal power plant. For example, Noracholi power plant is a coal power plant. Then if you are using a nuclear power, we call it that as a nuclear power plant. Then if you are using the diesel as the fuel, we call that one as a diesel power plant, right? All are thermal power plants, right? All are thermal power plants, but according to the type of fuel that we are using, we have different we normally use different names, right? So so basically what is the difference is only the fuel, right? Whether it's a coal or nuclear or diesel or naphtha, right? Even geothermal, only difference is the type of fuel that you are using. The rest of the thing is same. For example, in this diagram, so this you can see this side is the coal, but all the other things apart from this one, right, all of these are same for, that means all of these things are same for any thermal power plant. Basically most of the power plant, these components are same, but on this one can change, and according to that we have different names, right? Okay. Now let's we discuss on this component. So basically we are interested in 4 components, right, in a thermal power plant. The first one is the boiler. Now you have the boiler here, right? It's the boiler. Then we have the turbine, right? Then we have the condenser. Then we have a heat water pump, feed water pump. Now feed water pump is not indicating here. You have some kind of a device we call a pump. It's just a pump, right? What it do is increase the pressure of the water, right? So this is a feed water pump, the boiler, turbine, and the condenser, right? So these are the 4 components that we are basically interested on doing so, right? Okay, let me go each of the items step by step. So what the boiler do is, right, what the boiler do is it generate heat. It produce heat using the fuel, burn the fuel, and it generate steam, right? So you have the fuel burning compartment here. Then that heat goes into absorbed by the liquid, that means basically water, and that water turn into a gas, right? So most of the power plant, the working fluid is water, right? So what you have in here running in these tubes are water, right? So what enters to the boiler, right? So this is the entrance for the boiler, right? This is the water line enters for the boiler. So this is a liquid, and it has high pressure, right? Because we have pump here, pump the fluid to a higher pressure, therefore higher pressure and liquid state, right? Then what happened inside the boiler is the water absorb energy, then turn that water into steam, right? So what exit from there is a gas, so we call vapor, and it is high pressure, right? So boiler, you can think the boiler as a normal kettle, right? You know, you can boil up the water using the kettle. So what happened when it comes to the saturated temperature, you can get the steam out, right? So input is the water in liquid state, and the output is steam as a gas. So the same thing happened inside the boiler, right? So you have the liquid pump into the boiler, and exit from the boiler you get the vapor or the steam, right? Then the steam goes to the turbine, right? So turbine is a set of blade where it can rotate due to high pressure steam, right? So the high pressure steam enters the turbine. That high pressure steam turns the turbine, right? So again, it's set of blade, like you can think of it as a set of propellers, right? When the steam hit the propellers, basically the turbine turns, right? Then that turbine is coupled to a generator, right? When the turbine turns, it turns the generator, then the generator can produce electricity, right? So the next thing, when the electricity is transmitted to the transformer and transmission line, then to your homes or houses, right? Whatever things, okay? So, but in this case, we are not actually studying from this point on, right? We are not studying from this one. What we are interested in the turbine, and it produce work. That's the only thing we need, right? Generator, transformers, and transmission line, we are not actually dealing with those things, right? Then now we have produced the steam here and use the steam to turn the turbine. Then after that, the steam flows into condenser, right? Now this is a condenser. Why it is called condenser? Because it condenses. That means it change the phase. Now you have gas here. Again, what you exit from the turbine is a vapor, right? Again, vapor or gas, but it is the low pressure, right? Because there's a pressure drop, right? You have high pressure here, and in here you have low pressure. There's a pressure drop when the steam passes through the turbine, right? But we still have the things in vapor as a gaseous state, right? Then what the condenser do is remove heat, right? Q out, okay? What boiler do is Q in, right? This is Q in, right? Q in, that means the heat addition. So in here, heat rejection, right? Okay, right? So that means they remove the excess heat in the steam. At the process, the steam condense. That means water turn into a liquid, right? So we have the gaseous state here, then exit is the liquid. So what we exit from here is the liquid, in here is the liquid, and also low pressure liquid, right? So how do they remove the heat? Is using heat exchanger. So basically condenser is a heat exchanger, right? That means you change the heat, you remove the heat to a secondary medium. So what you have here is again a circle, again mostly it's a water circle, right? But the water line in here does not mix with the water line in here, right? So we have the cooling tower. So this is the cooling tower, right? Then you have the water in here, normal water, right? Then that water is pumped through the condenser such a way that that water that carries the excess heat, right, again to the cooling tower and sprinkle the things, right? And then it comes back, cool down in the cooling tower, again is pumping back. So you have a one water cycle in here, right? In this case, right, water is circulating in here, and this is another, this is the main cycle, this is the cycle that we are interested on, right? Which the working fluid or the working medium of the our cycle. Then the cycle in here is only for cooling purpose, right? So right, then the condenser at the exit of the condenser you have the liquid, and also you have low pressure. Then you have the pump here, right? Pump which pump out or increase the pressure. So you have the liquid enters to the pump is liquid, low pressure, then exit from the pump is liquid, high pressure, because pump is used to increase the pressure, right? So those are the four main components of any kind of a thermal power plant, right? And these are the auxiliary system, right? That means the coal burning, whatever the fuel you are using, that burning process is an auxiliary system. Again, this electrical system is auxiliary system, and again this cooling system, right? Cooling system is again auxiliary system that we are not actually interested on studying on these things, right? But in this course we are interested on boiler, turbine, condenser, and the feed water pump, right? Feed water pump. Those are the only thing that we are interested on studying on this course. Okay, so those are the basic working principle of any kind of thermal power plant, right? So again, what you have seen is the basically the four component. We have the boiler. Boiler we have the Q in, right? So boiler we have the heating in the inside the boiler. Then we have the turbine work out, and the condenser Q out, and the pump work in, because we need to pump the, that means we have to increase the pressure. For that we have to give work. Basically we use electricity to pump the water to a higher pressure. So this pump is you can think this pump as the water pump. You have domestic water pump in your home, so it is somewhat similar to this one, but of course it's much more complicated. But for the bean, you can think this pump is something like that, right? Now in our example, we simply draw these four components in like this, right? So the boiler here, Q in, turbine work out, right? Exit, work exit, condenser Q out, pump work in, right? So these are the four components, and we have the hot reservoir and the cold reservoir, right? Basically hot reservoir means the inside the boiler we have burning which produce the heat, and that is there. And cold reservoir means basically atmosphere, because we are rejecting the heat to atmosphere, right? So that's hot reservoir and cold reservoir. And all the other these four components are the components we are only analyzing in this course, right? Now if you consider these four components, right? If you divide this into like this in between, right? What you see in this side is gas or vapor, right? And this side is liquid, okay? And if you divide in this manner, right? Okay, this side is high pressure, and this side is low pressure, okay? Same thing can apply to say you can divide the same thing in this way, for this diagram as well, right? So we have the vapor side for vapor, that's gaseous state, and this side you have liquid. And if you divide in this way horizontally, you have the high pressure up there, and down you have the low pressure, right? Okay, right. So then what is we have in is the boiler and the steam turbine, condenser, and the feed water pump. So same thing we have discussed so far. So I want you to read these things out, right? Simply it tells what we have discussed, right? Okay, then we have animation. So I have given the link here, right? So I'm not going to play this animation in here, but I want you to stop this video or pause this video at this moment and go to this link and observe this animation, right? So it's explain the things much better, and also it gives you much more information, right? There are a lot of information in steam power plant, but of course you can grab what we have discussed so far, right? In there you can find the actual figures for boilers, turbine, and condenser, and the feed water pumps, right? I want you to find identify those four components, main components, right? Right, so I want you to go to this link and observe the video, right? Then again there's another one, right? How the turbine produce work, how the turbine turns the heat into work, right? Again the link is given here, right? So go to there and check how that works, right? So I'm not going to play these two videos here. If it is a classroom, if we're doing it physically, I would have played these videos, but right now you have enough time, so please go through it and observe those videos, right? Right, so this is how it's look like, the steam turbine. So we have the boiler. Now this boiler is somewhat different from the power plant boilers. This is boiler that normally we use in industrial applications, but boilers in power plant is somewhat different, right? Then this is the turbine. So from the steam goes from the boiler to turbine, right? Then so you can see there are a set of blades, right? So when the steam passes through this blade, this turbine rotate. That's mean making work, right? That's mean converting heat into work, right? Then it goes to the condenser. So this is condenser. So steam goes in this way, right? Steam goes this way, right? While it's going, so it cools down. So you have the gas here, right? So gas become a liquid here, right? Then this is the cooling water inlet and cooling water outlet, right? So this cooling water outlet goes into the tower, cooling tower, and cools down, then come back and again use it as a cycle, right? Then from there water goes to the feed water pump. So this feed water pump from there to again to boiler, right? So this is the basic cycle. Okay, right. So these are some of the pictures of thermal power plants, right? So I want you to identify these stacks. So you have one stack here, right? And there's a 1, 2, 3, right? So this one, let's say 0. This one is the exhaust stack, right? Where you burn the fuel, and the exhaust from that fuel exit from this stack, right? And these are 1, 2, 3 are cooling towers, right? If you remember, if we go back to our first, right? So this is the stack which output the exhaust gas, right? Right. This is the burning, after burning the coal, you have the exhaust gas goes through this stack, and these are the cooling towers. Cooling towers is basically cooling down this cooling water. So you have the cooling water running through here. So that's what the cooling towers do, is cools that water, the cooling water, right? Okay. So that those are these other kind of stacks, cooling towers, right? Okay. So you can, even in here you can see in this one we have 2 stack here for the gas, for the exhaust gas, and you have 1, 2, 3, 4 cooling towers, right? Right. So then what are these white smoke, right? White smoke. Okay, these are not actually exhaust gas, right? These are again steam, right? Steam, not from that main cycle, but the steam from the cooling cycle, right? Okay. So this is typically view, normal view of a thermal power plant, right? Then the next picture, this one, right? I want you to identify this picture, right? So this is one of the not one of the, actually the only coal power plant in Sri Lanka. This is a picture of a Morachole power plant, right? So you can see this stack, right? So this exhaust stack, 1, 2, 3. That means we have 3 boilers. So what you see in this building is the boiler. All of this building is boiler, right? You have one boiler, another boiler here. So boiler produce steam. Steam from this boiler goes to the turbine, and it's produce, one of these turbine produce 300 megawatt of power, right? And altogether we have 1, 2, 3 into 3 basically produce 900 megawatt from Morachole power plant. Right? Okay. Now you can't see the turbine here. It is inside the building, inside this building, right? But this building is basically the whole boiler, right? So there's a problem, right? So you have the exhaust stack, right? So in this case, in this picture, you have one exhaust stack and 3 cooling towers. Then in here also you can see this exhaust stack, this exhaust stack, right? There are exhaust stacks here, and you have a lot of cooling towers. But what about the cooling towers in Norachole power plant, right? So we have exhaust stack 1, 2, 3, but where are the cooling towers? Okay. Now, actually we don't have cooling towers in Norachole power plant because we are using a different way of cooling in Norachole power plant, right? What the Norachole power plant do is they pump the seawater for cooling, and then after cooling the condenser, they pump the things back to the sea, right? Okay. So most of these in these two cases, right? In these two cases, the cold reservoir is the atmosphere, right? In this case, in our case, Norachole case, cold reservoir is the ocean, right? It is the ocean that absorbs all the excess heat. In here, it is that atmosphere that absorbs all the heat act as the cold reservoir. In this case, Norachole case, it is the ocean that act as the cold reservoir, right? So we, for the cooling purpose, we pump the seawater and dump back that seawater again to the ocean, right? That's how they achieve the cooling in Norachole power plant, right? Okay, right. So let me move on. Then we can discuss about the Carnot vapor cycle, right? So we have our four components: pump, boiler, turbine, and the condenser, right? Then at the same time, I'm going to draw this one in a TS diagram, right? Temperature is entropy, right? So this is the first time we draw a TS diagram, right? So if you remember, we already drawn PV diagrams, right? If you remember, so this is the PV diagram for a pure substance, right? So this is our curve, if you remember, right? Then we have two pressures, high pressure line, high temperature, that's T2, then another secondary temperature, right? T1, that means T2 rather than T1. I hope you remember this one, right? So this is the PV diagram. So we have drawn PV diagrams, right? Then we have drawn T temperature and TV diagram, right? Then we have drawn P and V diagram, right? Okay. I hope you remember this curve, how we can get this curve. If you are not, please go to the biosubstance lecture and refresh your memory, right? Okay. So the TS diagram, the curve is the same, right? If you remember our famous curve, like this curve, right? That curve is the same, right? And instead of volume here, we have the entropy, right? Entropy here. And also, right, if you remember in the PV diagram, we discuss PV diagram, let's say this one A1 to 2, right? We discussed that the area under the curve, this area represent work, right? Likewise, in a TS diagram, right? Okay, likewise, area this under the curve represent Q, or the heat absorbed or rejected during the process, right? All of these can represent, may represent the work, right? Now it can be proved that this area is representing the total heat, but I'm not going to do that. We just use that as it is, right? Okay, right. So now let's we go into our components. We have the pump, boiler, turbine, and condenser, right? Then so the process start from 1 to 2 and 2 to 3 is the boiler, 3 to 4 is the turbine, 4 to 1 is the condenser, and 1 to 2 is the pump, right? But let's start from the 2 to 3, right? Because we are familiar with the boiler, therefore we start from the 2 to 3. So the 2, and same time I'm going to draw this one in the TS diagram, right? So this is our famous curve, right? And 2 to 3 is the boiler action. That means in here you have liquid, right? You have liquid and it is high pressure, right? So this is high pressure liquid, okay. So point 2 is here, so this is the point 2, and in the saturated line, so saturated liquid line, so you have the critical point here, right? So this part is saturated liquid line, this side is saturated vapor line, right? I hope you guys are remembered that one, right? So point 2 is here. What this do is convert liquid into gas, right? So you have saturated liquid into saturated gas. So what you have here is 100% saturated liquid turn into here 100% saturated gas, right? So this is liquid, this is gas, right? So 2 to 3 is a constant pressure. Now pressure line goes like this. Now this is one pressure, right? And so this is high pressure, this is the low pressure, right? That means your pressure line goes like this, there and like that. This is high pressure, and then this one you have goes like this, and this is low pressure, okay, right? Okay. Then what it do, 2 to 3 is a constant pressure. You can see this goes on the pressure line, therefore 2 to 3 is a constant pressure heat addition. So you have the Q in here, Q in, right? Constant pressure heat addition. So 2 to 3 is the constant pressure heat addition in a boiler, right? Okay, that's it. Then after going to the the boiler, you have the gas, then gas passes through the turbines. So that pass we call it as an isentropic expansion, right? You remember when we discuss about the when we introduce the isentropic process, we talk that compression and expansion are isentropic, right? Okay, so what you have in is a isentropic expansion in a turbine, right? 3 to 4 isentropic expansion. So what is isentropic mean? Entropy is constant, right? Entropy is constant, therefore you have fixed entropy, therefore this entropy should be constant. Then you have the straight line, a vertical straight line going down, right? So 3 to 4 is isentropic expansion in a turbine, right? While doing so, while it expands, it produces work. So what we have in here is W out, okay, work out. Then so 2 to 3 constant pressure heat addition, that's okay. Then 3 to 4 isentropic expansion, right? Now again let me talk about the condition here, right? So we have 100% liquid here, saturated liquid, 100% liquid. Again then what happened, it's absorb the heat, then convert the liquid into gas. While it goes through from 2 to 3 water molecules, so water molecules become gas, right? So in here you have 100% gas, right? 100% gas here. Then when it goes 3 to 4, right, you can see 3 to 4, while it's going down, in here what you have, we have mixture, we have gas, we have liquid plus gas, right? So we are in the mixture region now, right? Not on this line, therefore we have mixture. The larger portion is the gas, because we have the larger portion here, so this is the gas portion, right? And this is the liquid portion, while it start from here going down there, right? The liquid portion increases. You can see this is a liquid portion, again liquid portion, while it goes there, liquid portion increases, right? So in here we have large portion as the gas and some liquid portion, right? That means enters to here is 100% gas, but out here is a mixture. That means vapor plus liquid, right? Okay, then we have the condenser. Again condenser, this section is constant pressure. This is you can see the pressure line, this is a constant pressure. Okay, let me clean these things up. So this is the constant pressure, right? Then this is Q out, we have Q out here, Q out, right? Okay, that's mean you have mixture here, right? Then again rejecting the heat and condense the gas into vapor, right? Again you have mixture here, and again in here also you have mixture, but the large portion is liquid, right? Large portion is liquid, less portion is the gas. So this is the gas portion and this is the liquid portion, right? Liquid portion increases and gas portion reduces, right? Okay, then after that we are pumping the things. We have the pump action, right? Again what you have in here is the mixture, enters to the pump is gas plus liquid. Liquid is the large portion, right? Then pumping to a higher pressure such a way that you have 100% liquid, right? That means you are pumping this one. Again constant entropy, therefore this isentropic, we call isentropic compression in a pump, right? 2 to 3. In there you have you can stop at exactly at this point, that means 100% saturated liquid, right? Okay, so that is the cycle, right? So in this cycle we have Q in here, Q in, this is Q out, this is W out, right, and W in. Okay, those are the, right. So this is again, if we come back, pump action, boiler, turbine and the condenser, right? Those are the 4 processes, right? So then the efficiency for this, now this is you remember we talk about the heat engine. Now this is a heat engine, right? So we can write the neta, that's the efficiency for the heat engine. Now this is the that we have derived, neta for Carnot equal 1 minus T minimum divided by T max. So let's try to derive this one. So this is the heat engine, therefore we can write the neta for efficiency for the heat engine, right? Neta heat engine equal W net divided by Q in, right? If you remember that one, right, from the last session, right? Then we can write W net, right, divided by Q in. So what is the Q in? Q in, let me say this is T max, temperature max, and this is the T minimum, and let's say this one SA and this point SB, right? So we can write Q in equals all the area. So this is the Q in, right? This is the process Q in, no, right? All the area under this curve, that's mean all this curve, right, like this, right? All this is the Q in, right? So we can write Q in equal to T max times SB minus SA, right? So we can write this in this way, right? And also we can write Q out equals to T minimum times SB minus SA. What is Q out? Q out is this, right? This is the Q out. Okay, this Q out, right? Okay, so we know this one. Now Q in we know, Q out we know, right? Let me try to find what is W net, right? Now from the first law of thermodynamics, you know delta U equal to Q minus W. In internal energy change equal to Q net. Q means net heat minus net work, right? Since this is a cyclic process, right, that means you start at some point and come back to that point. Therefore for this cycle, the whole cycle, delta U equal to 0, right? Why? Because there's no change in internal energy, because it is a cyclic process, right? Therefore we can write Q equal to W, right? Q here, so this is W net, right? And Q also Q net, right? Q net equals to Q in minus Q out equals to W net, right? Okay. Then from, let's say this is A, from this A we can substitute for here, right? So what we get is neta equals to Q in minus Q out divided by Q in. So this become 1 minus Q out divided by Q in, right? Okay, then Q out is this, Q out is this, Q in is this. That means we have to divide this Q out divided by Q in. If you substitute this one, we can get neta equal to 1 minus T minimum divided by T max. Okay, so that is the derivation for Carnot for this cycle, efficiency for this Carnot cycle, right? Okay, right, so let me clear these things up. Right, I hope you guys understand how we can come to this equation, right? Now let me discuss about this equation a little bit, right? So the Carnot engine, the Carnot cycle is considered as the most theoretical efficient cycle, right? Theoretically gives the maximum efficiency, right? That means it is the Carnot cycle that gives the maximum efficiency, right? Actually the Carnot engine, we cannot actually implement the Carnot engine. There are some problems, we will discuss about that one, but in theoretical means Carnot engine is the one that gives the maximum efficiency, right? In all the thermodynamic cycles, all the thermodynamic engines and heat pumps, we talk about something called Carnot engine. Carnot engine is a theoretically maximum efficient. That means no other application in the world can achieve Carnot efficiencies, right? For example, let's we discuss, let we look on the petrol engine or diesel engine or whatever the engine. They have their own efficiencies, but they are unable to exceed the Carnot efficiency, because that is the theoretical maximum that we can achieve, right? Is the Carnot efficiency, right? So this one equals 1 minus T minimum divided by T max. So to have a maximum efficiency, right, that means to increase the efficiency, what we can do is to lower this portion as far as possible, right? That means if this becomes 0, right, then we can achieve the 100% efficient, isn't it, right? But to become this one 0, so we have the T minimum, right? You have the T minimum divided by T max. To this one to 0, T max should goes infinity, isn't it, right? To have maximum efficiency, this whole part need to goes to 0. To this part to go to 0, you need to have T max go to infinity, right? You can see, now you can see it, that means the temperature should be infinite, so that is not possible, right? In all the practical cases, we can't have infinite temperatures, right? Therefore this is always has a limit, right? That means this one has a limit, right? This one is a finite number, we can't have this one goes to 0. This is a finite number. That means all the efficiency neta is lower than 100%, right? Okay, that means you have 1 minus something, that 1 means 100, 100 minus something, that means all the efficiencies, I mean the efficiency of Carnot cycle is below than the 100, right? So this is the theoretical, most theoretical, that's what I say, right? That means you can assume anything that you want, right? Even so, you can't achieve 100% efficient, in this cycle, right? That's why the Kelvin Planck statement, they said you can't convert heat into work 100%ly. You can't do that, right? You can't convert heat energy to 100% work in the Kelvin. If you remember the Kelvin Planck statement, so that statement proves in here, right? You can't have 100% efficient in here, right? Okay. And to get the maximum efficiency, of course, this part need to be low as possible, right? Okay. To have the maximum efficiency, T minimum divided by T max should be low as possible. To have that, T minimum should be low as possible, T maximum should be large as possible. That means the difference, that means T max minus T minimum should be large as possible to achieve highest Carnot efficiency. That means the difference, if you have larger difference, you can achieve good efficiency. If the difference is low, then you can't have great efficiencies, right? For example, let's say in T minimum, so T minimum is mostly atmospheric temperature, right? 27 Celsius or something like that, right? So we can't go beyond that one, no? So normally it is at heat sink is the atmosphere, right? Therefore this is the atmospheric temperature, and T maximum is that the one that we can control, right? So the thing is, larger the gap between the larger the difference, neta is higher, lower the difference, neta is lower. That means, for example, let's say T minimum equal T max equal T minimum, then this one goes up, this one 1, then neta is 0. Right? That means your T max and T minimum are the same. That means same temperature. This is 0. Neta is 0. You can't get the conversion, right? You can't convert heat into work. That's what. So you need to have a difference. Then only you can convert heat into work, and the larger the difference, you can convert lot of amount of heat energy into a work, right? Okay, that's what this tell, right? Okay, right. So that is Carnot vapor cycle, right? Then why we can't produce, why we call the Carnot is a theoretical construct, is because we have some difficulties. Actually, we can't implement Carnot cycle in practical applications. There are two problems, right? One problem is this. So the first one is this point 4, right? This point. Now actually not point, the whole process 3 to 4. Now if you remember, what we have inside the turbine is set of blades, right? Set of blades, right? Now what happened when the steam goes from 3 to 4, you can see when it goes from 3 to 4, liquid portion increases, right? You can see the liquid portion increases. That means when the steam flows, it produces droplets, right? That means water droplets, right? Now the steam travel very fast with that droplets, right? That means water droplets. So what happened was, these droplets hit on the turbine blades, right? And it damaged the turbine blades, right? You have droplets hit on the turbine blades and damage the turbine blades. So this is one of the problems that we are having, right? So the better way to work on the turbine is to having all the steam, right? Without droplet, if you can pass the steam, only the steam from through the turbine, so that is the best thing you can do, right? But if it is form droplets, then it will damage the turbine blades, right? So this is one practical problem that we are having when we try to implement the Carnot cycle. Okay, that is the first problem. Then the second problem is at here, number 1. What we have is a pump, right? And what we have in here is a mixture. Again, mixture, mostly liquid, right? Mostly liquid portion is higher in here, gas portion is low. But again we have problem, And now what we need to do is increase the pressure. So we have the low pressure here and we have the high pressure here, right? Okay, high pressure and low pressure here. Okay. Now if it is liquid, we can use a pump, right? If it is 100% liquid, then we can use a pump, like the domestic pump you are having in your home. We can use a pump to increase the pressure, right? If it is a gas, right, if it's 100% gas, we can use a compressor, right? We call it compressor. I'm sure you have seen the compressors in, in tire shops. They use compressors to fill up their to the tubes. Likewise, you have compressor. So then you can use a compressor to increase the pressure. What we have in here is a mixture, right? But unfortunately, we don't have equipment to increase the pressure of a mixture, right? Again, that is again a problem. What is preferred is either 100% gas or either 100% liquid, right? Therefore, compressing this one, okay, increasing the pressure at this point is again a problem, right? Another problem is that how we can stop this process in this point. That means you have to control this process, no, 4-to-1 process. That means condensing, the cooling process need to be controlled such a way it will have this composition, right? It will stop at here. Again, that is also in engineering wise, it's somewhat complex. It's hard to achieve. So, right, therefore, because of these practical problems, practical difficulties, we are unable to construct engine using Carnot cycle, right? Okay, so that is what is explained in here in these two, right? Okay, I want you to read it out, right? Therefore, to what the engineers do is they invent another cycle called Rankine cycle, right? Now we have two problems, right? That means this is a problem, so this is a problem, and again this is a problem, right? So what they do is they correct these two problems in such a way so you can have a different cycle, right? Okay, what is this? The solution is this, right? Instead of expanding, now this is the boil action, the heat addition. So this is the heat addition. Instead of stop here and goes from there, instead of doing this one, we further heating until it reach the superheated region. So this is superheated region, right? Okay, now this boiler start from here or to the here, then again further heating the things up until it get superheated region, right? Then superheated steam flows to the turbine, right? You can see now mostly we have gases. There are some small portion here where the droplets forms, but that is okay, right? That is okay. But in here, starting from, we have droplets, all these droplets, but it's not here. We have small droplets form here. That is okay for the application. And what the engineers do, they further heat it, make it superheated steam. So what you exit from here is superheated steam. Then that superheated steam goes to the turbine, then isentropic expansion, right? Then it's come back to number 4, right? Then in condenser, instead of stopping somewhere here, it further cools down until it hit the 100% saturated level, right? Then what you have is 100% liquid. Then we can use a pump to pump the things up, right? Okay, right? So then this is the pump action 1 to 2. You can see the pressure line. This is one of the pressure line, high pressure line. This is high pressure. This is the low pressure, right? So okay, then so further cools it up to, until here. Then pump the things up to number 2. So the 1 to 2 is pumping action. You can see very small amount there, right? This is pump action, right? Then 2 starting from here all the way to here and to here, right? This means so this is the boiler. So 2 to 3 is boiler action. So we are supplying the heat until it start from here all the way to saturated level, and again saturated level gas until it comes superheated level, right? So this is the boiler action. Boiler start from here to here to here to here, right? Then the turbine, then come condenser, then the pumping, right? So this is we call the Rankine cycle, right? Now it is the Rankine cycle that operates in most of the the all most of the thermal power plant, right? Even in Noracchole, even in Kelavara, right? Whatever the steam power plant, you have Rankine cycle, right? Okay, so this is actually a theoretical. This is not a theoretical construct. This is actually a practical construct, right? Okay, so the same thing goes here. 1 to 2 is isentropic compression in the pump. 2 to 3 constant pressure heat addition. Same thing as the Carnot cycle, right? Then we have 3 to 4 isentropic expansion in the turbine. 4 to 1 we have constant pressure heat rejection in the condenser, right? So the Q in. So in here we have the Q in, right? So 2 to 3 is the Q in, then work out, Q out, work in, compression, right? That's the 4 processes, right? So that is the Rankine cycle, right? Again, then let me construct for the neta efficiencies, right? Now with that we can say work done. Let's first we derive these equations, right? Okay, then Q in, we can write Q in as, that is the boiler. So the boiler action is Q in. We can write H3 minus H2. That means enthalpy at point 3 minus enthalpy at point 2 equal Q in. Now how we can write this, right? Where we can get this, right? Q in, that means the total heat energy supplied in the boiler equal to enthalpy difference, right? Where we can get this? If you go back to the definition of the enthalpy, right? Right, if you remember this one, right? Enthalpy is the measure of the total heat energy absorbed or released in a thermodynamic cycle, right? Total heat energy absorbed or released is equal to enthalpy difference. So this is where we get that, right? Okay, that means we can come back. Okay, right, so the Q in, therefore Q in we can write, so this is the heat energy absorbed is equal to H3 minus H2. Likewise we can say Q out equals to H4 minus H1, H4 minus H1, right? Okay, then W out we can write H3 minus H4, right? W out H3 minus H4, right? Okay, then pump action, this pump action, that means W in, you can say W in equal to H2 minus H1, right? H2 minus H1, okay, that is pump action. Same way we can write the pump action, right? W in, if you remember in PV diagram we say work in P delta V, right? P delta V is the work input, but we don't have delta V here. Instead we have two different pressures, so V is the same, right? We don't have delta V, therefore we can write this one V delta P, V delta P. We have two different pressures now. Pressure is, so this is for the constant pressure, right? W in is the constant pressure, but we don't have constant pressure, therefore we can write V delta P. Instead of P delta V we can write V delta P. This is work in, right? Okay. So yes, so that is what in here as well, right? So pump work is V delta P, and q in is this, q out, w out is this, q out is this. So we know all the things. Therefore we can write the thermal efficiency of the Rankine cycle is this one, neta equal w net over q. Then also we can write w net equal to, so if you remember we have w net equal to q in minus q out, right? If we substitute this one, we can get 1 minus q out over q in, right? So one q out is known, q in is known, right? These two are known, q in, q out. Then we can find the neta value, right? Okay. Right. So these are the equations. Right. So again we can say if we need w net equal to q in minus q out, or we can say w turbine out minus w pump in. Right. Okay. So with that we have an example number 5 and example number 6, right? So example number 6 is a past exam question, right? So this is a past exam question, right? And example number 5. So I want you to work with these two examples, example number 5 and number 6, and try to work it out. But of course I will make a separate video, a tutorial video, how to work on this example, right? So let's we stop from this point, and I will make another video showing how we can work on this example, right? Okay, thank you.